So welcome to day 12 of the month of ML with the Hacker Hustle. And today we're going to be using this data set for object detection to build a machine learning model that will detect people in photos. So to cover this data set, firstly, you can find this at my GitHub. If you just go to datasets and S40 datasets, this is the Stanford 40 dataset, which consists of a bunch of images and a bunch of annotations. So in the images, you've got all these people. Every image has a person in, and you also have a corresponding annotation file for each of those images, which is an XML file within which there is the basically the details of where the bounding box, which bounds that person in that image, should be placed in the image. So to look at the data set, without saving that, so to look at the data set, firstly, if you just want to, you can just download this, git clone this, and then add that folder, the datasets folder, to your Python path so that Python will search for files there. And then the code in there looks like this. So basically, so when we create this dataset class, when we create an instance of that, we define where the images and the annotations are. As long as you put that dataset repo in your home, that'll be correct. Otherwise, you just need to adjust that slightly. Basically, so we list everything in those folders. We sort them so they should line up, and then we basically, to make a data set, we need to define two things. One is the get item. So this tells us, okay, how do we return a supervised pair of the image and the corresponding bounding box for that image? And we also need to define the length, which defines, it tells you how many examples are in the data set. There's also this helper function here, which is used when we want to show the when we want to show an image, basically. Firstly, when we get images back from the dataset, we want them to be a torch tensor, so we can pass that directly to our model. We don't want them to be an image, or we don't want them to be a list of the labels. We want them to be a torch tensor. So when we get an example back from the dataset and we actually want to visualize it, well, then we need to convert it back from a torch tensor to a Python image library image, and then resize it potentially so that we can so that it's a visible size, and then we'll draw the rectangle on that. And to do that, we need to basically get those coordinates out of each example, and then adjust them slightly, because the way that they're returned from the dataset is as the center X and center Y position of the bounding box, and the width and the height of the data of the bounding box. But what this draw rectangle function wants is the X min, Y min, X max, Y max in a pair of tuples. So we just need to unpack that using this bounding box to return it like this. And then, so there's something wrong here, and we're going to fix it right now. There's something wrong with this data set. So when I run it, so yeah, in this folder, in this file, I'm just importing that data set. I'm importing the get data loaders function from AI utils as well, which again you can find just here. So in that, there's a file which gets you data loaders, rather than have to write all of that out. So I'm making some. So I import the get data loaders. I use that to get the data loaders for our training set, validation set, and test set from the data set. And then just going, just basically getting the first batch in the training loader will show that batch, because this S40 dataset file also has a function in called show, and when you call that, it will show you an image with the corresponding bounding box. So if we run this now, we'll see. So I just need to remove that breakpoint there. Okay, cool. So there you go. We see an image and we see the bounding box, which locates within the image a person doing some action. So, but then we'll see if we run that a few times. Well, that's not quite right, is it? And again, you see like that's not quite right. It's not quite right. It's not quite right. Neither's that. It's a bad run here. But basically, some of them are right, like the first one, like that one. Some of them are wrong. So, and then a problem like this could happen in a data set that you're building. So, let's fix it. So what's wrong? Okay. Well, the reason. So basically, what we're doing in this file is we're getting is basically listing everything in those two directories, where we think the images are and where we think the annotations are. So that again looks like looks like this, where there's annotations and images here. So we're just listing everything in those two folders. Where we've got all the images there and all the annotations in the other one. And so what I've done down here is just printed the image names and the so when we get an item, let's just break it there and check that the image name that we're getting corresponds to the annotation name. So they should have the same prefix, right? So if we look in that data set, one of them is applauding _003.jpg, and then in the annotations file, we'll have applauding _003.xml, okay? So we want to obviously be looking at the correct XML file, which has the same prefix, as we are the image, okay? So if we run this now, I'm just going to break it after we print the image name and the annotation name. So when we run it, what you get is, well, those two, they aren't the same. They're just one off. And again, they're one off. Again, one off. Yeah, again, one off. But sometimes they're not. Sometimes they match up, okay? So what's happening, right? Well, what we're doing when we're getting the item is we're getting an item of a certain index. So now, if these lists of the annotations and the images say one of those folders is missing one of the images, well then that's going to mean that say we're missing the first, we're missing the annotation 000. Well then the first annotation, that list is going to start with annotation _001, and then the image is going to start with 000. So if we get the same index from both of them, then one of them will be the photo corresponding to 001, whichever way around I said it, and the other will be the bounding box corresponding to 000. So they won't match up. So I think that's the problem. So let's just print. So when we create this data set, let's just print the length of them to check that they're the same. And if they're not, then that could indicate that is the problem. So we'll go back in this file, run that. Cool, right, so yeah, you can see that the, which one we print first, image names, the length of that is one less than the number of annotations that we've got, okay? Well, so we've deleted one Yeah, we deleted one of the images, or there's just one less image. I actually know what's happened. So when I downloaded this data set, there was one image in the images folder for some reason, which wasn't a color image. It was a grayscale image. So I only had one channel instead of 3 RGB. And so obviously, I mean, that's just not meant to be there. That's anomalous. It's totally different. It's from a different distribution to the actual to the color data if we want to use color images. So so that's not useful, and so we want to delete it from the data set. And so so removing that obviously means there's one less image in there, which means that if we refer to every image in the annotations in the image by index, well, then they're all going to be shifted slightly by 1. Okay. So again, if you got any questions, put them in the chat, and I'll answer when I can. So right now we need to fix that. Well, so what can we do, right? We could figure out which item is not in the images, and then just remove the corresponding annotation file. Another way that we could do it is, we know we've got all of the, well, we know, so we've got more annotations than we have images, right? So somewhere, if we're going to get an annotation where there's no corresponding image, but if we just got the image and we took, say, the name of that image, the prefix before the file extension, then if we just got the name of the image and then used that name to find the file with the corresponding annotation, then we know that we'll have that file, because we've got, we know we have all of the original annotations, but not the original images. So I think that a better way to get the annotation name would not be to index the list of annotation names. It would be, in fact, to annotation name is equal to, what we'll do. So we've printed this image name here. If I run this again, now that I've removed that. So here we get that K, and then so here's the image name. Okay, right? Well, we know that the annotation name is going to start with this, right? Well, actually, it's gonna be this / annotations / jumping _0015.xml. That's what that's going to be. So we need to somehow set that. Okay, cool. So instead of listing what's in the directory, because we know there's one too many in there, what we will do is we'll do self.annotation names is equal to, so we know we've got all the images, right? What we're going to do, and in this init function, we've got this annotation directory, which is that home /dataset /s40 /annotations. So what we're going to do is we're going to join together. So os.path.join, so using the operating system path library, join together annotation directory, and also the name of so the name of the file, which in this case would be jumping _015. So the file name for file name in self.image names, okay, right? But that file name is going to be this whole thing. So really what we want to do is we want to basically just get this part out of it. And then we'll add a .xml on the end of that. So plus .xml. Well, how are we going to get that? Just the name from the part from that file name. Well, we can do firstly we can do .split. So we can split that file name every time we see a slash, and then we know when we get that. Well, if we split it every time we see a slash, it's going to return us a list, and the last element in that list will be the last thing which was after that slash, which will be that. Okay. So we'll say. So we get the last element from that, and then from that we'll do .split again, and we'll split it on the dot. Okay. And then we know there'll only be one element in there, so we'll just get that element, and then we'll add XML. So that should be good, right? So now let's go back there and run that. Yep. Obviously, I don't want that to be that anymore. So we've done a different implementation, so do that. Cool, now it looks like they match up on the first try, so just to check that's not an anomaly. Yeah, cool. They seem to be matching up now. Alright, good. So now let's just remove that breakpoint. And then run that again and show it. Okay, cool, that looks good. First try. Yeah, good again. Yeah, okay, good again. So now all of these images have a correct associated bounding box. Okay. Cool. So now, now what we're going to do is we're going to build a convolutional neural network to try and predict those bounding boxes given the image. Okay. So. Cool. Alright, so what we're going to do is we're going to import Torch, our deep learning library, and then what we're going to do is we're going to, so we've made the transforms. So when we're doing those transforms, when we read every item, we're resizing them to 512 by 512, and then we're transforming them to a tensor. So let's make that smaller actually, just to make the problem a bit easier. And okay. Okay, so let's make our model. Let's make detector. This is going to inherit from torch.nn.module because it is a neural network. When we start that up, when we construct it, what we're going to do, we're going to take in, so let's say we want to be able to switch between doing this detection for grayscale or color images. So we'll say channels equal to 3 by default. So by default, we're going to do color images. And then what we'll do is, well, firstly, we'll initialize the parent class. So just to set up the stuff that makes us be able to do some helpful stuff with this model. Blank line end of file. Okay. Yeah. So then we'll define the layers. So we'll say self.layers is equal to torch.nn. Actually, you know what we're going to do? We're going to firstly do some convolutional layers. Okay. Torch.nn dot sequential. Okay. And then the first layer that we're going to do is we're going to do a torch.nn.conv2d, and basically these convolutional layers take in, well, what's the number of channels I'm going from? That's 3 in this case. Well, in this case, channels. And then what number am I going to? So let's just make this a bit more parametric up here. And then we'll just say channels 1 is equal to 32. So we'll have four convolutional layers. So that'll go from the number of channels we start with to the number of channels at the end there. So what it's going to do is going to form 32 feature maps from the 3 channels. It's going to stride convolutional kernels all over that image, making linear combinations of the pixel intensities in the image, corresponding to the weights in each of those filters, which we'll learn. And then it's going to put that single linear combination at one particular location as a single value in the single channel feature map in the next layer. And it's going to make 32 of those different feature maps. So I have those 4 convolutional layers, and we'll just swap out. Okay, yeah, cool. Just give those layers the right indexes. Yeah, that's cool. So we're going from that, okay, and then we're also going to swap. I highly recommend you use Vim. My editor has a Vim emulator, so I can do all these commands, which make things faster. Channels 2. Okay, I probably don't really need to be using them here. So cool, we'll go from channels 1 to channels 1, channels 2 to channels 2, channels 3 to channels 3, and then output channels 4. Okay, right. So in this case they're all the same, but we could easily change them now. Whatever, probably not a good idea. Cool. Let's see what happens like that. Right, so now we have gone through all these layers. Well, we need activation functions between those layers, so we'll do torch.nn.relu. Okay. Okay, cool. So we've got all our convolutional layers and then a ReLU activation layer between each of them. And then after we've done all those convolutions, what we're going to do is we're going to end up with a long but low resolution. Well, with a lot is what I mean. A lot of low resolution feature maps. So they'll have a size of much less than I think 128. They'll be much smaller because convolution always decreases the size of the input, but there'll be a lot more of them. So there'll be 32 in this output channel, and there'll be 128 in the first transformation. Okay, so I've forgotten, we actually need the 2 more parameters, which is the kernel size that we're going to start with here. So we'll say just do a 7x7 kernel. Okay. Okay, so we've got can use 7x7 kernels in all of them. and then we can also specify the stride, which is the step size between each kernel, but I don't think you need that one by default. So let's just go without that for a sec. Now what we'll do is, after you've done the convolutional layers, we're going to pass it through some linear layers, fully connected layers. And again, that we torch.nn.sequential, and then we'll just have torch.nn.linear and torch.nn.relu, and torch.nn.linear again. And this needs to know, well, how many numbers am I going from? How many actual values are there in that full stack of the final layer activation maps? So both, so that'll be the width times the height times the width and the height of each feature map multiplied by the number of feature maps. But I can't be bothered to compute that here. Or QuickTime, what will it be actually? If we leave that stride as 1, we can compute it as a quick exercise. So we've got no padding, so we're starting with our kernels in the top left, and then moving them across until they reach the other end. With a 7x7 kernel, that means that the kernel will start 7 pixels. The center of the first convolutional kernel on the image will be 4 away from the side. So if you put a 7x7 kernel right in the corner of an image, the center point has, it's the center of 7, so it's 1, 2, 3, 4 from the side and the top in this case. And then when we move to the other side, well, it's also only going to be able to get to the 4th last pixel. So that means we're going to lose 3 from either side, which means every time we do a convolution, we're going to go down by 6 in the width and the height, right? So if we start off by 128 and go down by 6 each time over 4 convolutions, 4 times 6 is 24. That means we're going to have a 104 width and height feature maps, activation maps on the end. So that's going to be 104 times 32. Do I know that one? Yeah, 1043. Yeah, well, we've got 104. 104 times 10 is 1040. That times 3 would be 3120, and then plus 208, 3120 plus 208, 3328 should be the number there. Just for fun, I might be wrong. And then let's say we'll go to 128 output units of that layer, and we'll go from 128 output units there to let's say down to 64. Then we'll do another ReLU, and then we'll do final linear layer. And this one needs to go from 64 to the number we're actually trying to predict. We're trying to predict for each image a width, a height, a center X, and a center Y location for the bounding box, which is 4 numbers. So we need to go to 4 numbers there. And also, what we're trying to do is, if you look at the labels, so these are the labels for a batch of size 3. So we've got those 4 numbers. They're all less than 1, and that's because they're proportional distances, they're proportional widths, well, the proportional X and Y positions relative to the overall width and height of the image, because those can differ between different images, as you saw. So, well, actually, as you didn't see, because when we're showing them, we're resizing them all to be the same size. But the actual input images, they can be different sizes. So during the within this data set, we've we've divided them by, we've normalized them over the width of the image and normalized them over the height of the image, so that these four numbers, x, y, w, and h, they all turn out proportional. So we need to be predicting proportional numbers as well here. Well, with linear layers, we have an unbounded output. It can be whatever. So to put it in the range 0 and 1, so represent proportion, we can do torch.nn.sigmoid. And then that should be good. Alright, so now we'll define what happens when we do a forward pass. On some example x. Well, what happens firstly, we'll pass it through the convolutional layers, and then after we've done those, we'll pass it through the fully connected layers. But we can't quite just pass it directly from the convolutional to the fully connected, which is the whole reason I've separated them up here. And the reason for that is that the linear layers, these fully connected ones, they take in vectors. If you remember the standard 2D drawing of a neural network, it's nodes in different layers, and each of those layers of nodes represent a vector. So we need to reshape this, the output of this convolution, of these convolutional layers, which is still a tensor, in this case a 3D tensor. Then we need to reshape this x. So we need to flatten that tensor into a vector. So we'll say x equals x dot view. Now, okay, so what's the shape of this x here, right? Well, is the way they're passed forward is in batches. So actually, are they all passed through the forward at once? Yeah, I think they are. So a whole batch is passed through the forward at once. In our case, the forward has a batch size of 3, right? So this x is going to have size 4. So we're gonna firstly have the first dimension on this x is going to be 4. It's going to have 4 elements, right? And each of them is going to be the output of the convolutional layers for each of those, for each element in the batch. And then within each of those elements, well, there we've got a 3D tensor, right? So here we've got, like I said, 108 by 108 by 32 feature maps, okay? So, but then the problem here comes, well, yeah, we could just say, okay, cool, so I want to reshape it, so I've got 4 vectors, and I don't care what the output size is, right? As long as it matches. That means, like, just calculate it yourself, Torch. The problem with that is that sometimes the dataset size, the number of examples in the dataset, is not an integer number of this batch size, which means that you can't hard code the value there, because we might get to the end of the dataset and there'll only be 3 examples left. And that means we're going to have a batch of size 3. So if we do size 4 there, well, then this number will be different. And this is really the one which always is going to be the same. And this is the number which we should hard code, the actual number of activations produced by the convolutional layers. So we won't hard code that one, but we'll say, okay, the batches can be whatever size they want. And then the output here, if my calculation is correct, should be 32, 33, 28. That's how many elements we should have for each example. So after we've done that, we pass through the fully convolutional layers, then we will just return that x, okay? And that should be our prediction. So now, back to another library I'm going to use. So AI-Utils has a file called training, which again is in the GitHub here. It was there, wasn't it? Yeah, which is here. It's got this file training. This basically just means that we don't have to write these training loops out, because they're always the same, whatever model you're doing. So we're going to use this. Well, we're going to use all of these actually. So firstly, we're going to get our loss plot to plot how well our model is doing. So So yeah, here we'll do loss plot is equal to get. We need to import that, don't we? So they're the three functions which are in here: evaluate, train, get loss plot. Okay. So actually that doesn't return us just that, does it? It returns us the figure and the axis. So we'll do so we get the figure and the axis from that, and then we'll just do so we'll say number of epochs, let's say just one firstly, and then we'll say for epoch in range epochs. So every time we go through the whole data set, that's one epoch. What we're going to do, well, we're going to train our model, which we haven't instantiated yet either. We haven't created a bunch of things actually, so let's do that. So we've got some convolutional neural network, and that is this detector. Takes in the number of channels, equals 3 by default. We could even set that dynamically by looking at by reading in an example from the data loader and then checking its channel dimension. But whatever for now. So we'll train that model. What's the next thing that this function takes in? Takes in the data loader. So what is the data loader? The data loader is that train loader. Train loader takes in the criterion, which we haven't created yet. So the criterion we're going to use, our loss function is going to be, it's going to be the mean squared error loss. So basically, we've got those. We've got some continuous outputs. Although they're all between 0 and 1, they are continuous. Okay, the four numbers we're trying to predict, the proportional center x and y positions, width and height of the bounding box, they're all continuous. So what we're going to do is we're going to predict numbers within that same range, and then we're just going to take, well, what's the difference between those two numbers, and then the mean squared error loss for each of the loss for this for each batch will be the mean squared error between the difference. So you take the difference between the x, y, width, and height for each image. You'll square each of those numbers. You'll sum them up. You'll sum them up over all of the the examples in the batch, and then you take the mean of those. So the mean over the batch. So divide by 4 in this case. Divide by the batch size, and then that's a measure of how wrong your model is. So we're just going to try and look at that function, follow the local gradient, and update our model parameters accordingly using gradient descent. Or using Adam specifically as an optimizer. So we'll write that here. Make our optimizer torch.optim.adam. Well, which parameters is this going to optimize? It's going to optimize the CNN's parameters, and that CNN has that method which returns all the parameters because we inherited from torch.nn.module, and we initialize the parent class so that it tracks all of these layers which are modules for the neural network. Okay, and we'll just specify a default learning rate or starting learning rate. With Adam it can be whatever, because it will always be decayed down to a suitable value for convergence, but best to start there anyway. So yeah, let's continue filling this in. What does it need now? It needs the criterion, it needs the optimizer, it needs what epoch are we on, it needs the figure, it needs the axis, it needs the, I'm just looking over here now, it needs the training losses, so we haven't instantiated them yet. So we'll say train underscore losses is equal to some empty list, and then we'll say validation losses is also equal to some empty list. And then we'll do train losses here. And then yeah, so there's also this this module timer. Well, there's this timer, which is the profiler, which is also in AI utils. Basically tells you how long everything is taking, and helps you optimize your model. So it's helpful to have one. So what we'll do is we'll just import that again from profiler, import profiler. Cool. Right. So that profiler is this thing. So you start it up, you tell it to start tracking an event, then you tell it to stop tracking an event when that event finishes. It calculates the time between those things and puts them in a profile, which we'll see at the end. I've already explained that in another video, so I won't go over it now. So yeah, we'll say we've got that set up. May as well create that profiler up here. Timer, actually we'll just call it P. P is equal to profiler, right, that is going to be good. Yeah, cool. And then so yeah, then we can do something like p.start. Just give it the event name, so like making transforms. It's really easy to use. And then whenever that event finishes, you just go stop. So p.stop making transforms, and then that will calculate a difference between the time that those two things happened, and put that in the profiler. Then we can also do p.show just to illustrate that, just to remind you how that works. So run that. Yep, cool, good. Well, so basically when we do p.show, profile.show, it tells you, well, this event took averagely this long, so 1.1 times 10 to the minus 5 seconds, and it was called once. Okay, and you can do that in the same way for any other part of your any other event that you want to track in the code, whatever that might be. So in this training code, it's called twice here. So it's called there to start. So it says forward pass. So you can track like, well, what's the speed of inference of your model? How long is it actually going to take when I deploy this to pass something through the model? So, and then we'll just pass that that profile to that thing there. Okay. So at the very end, when we've done all our epochs, what we'll do is we'll do p.show again. Okay, so then we'll get back that profile of the code. So once we've done a training epoch, we will do a evaluation. So yeah, we'll evaluate on the validation loader. So yeah, it takes in, okay, there we go, CNN model. The data loader is the validation loader. Same criterion. What epoch are we on? What's the figure? What's the axis? And then what are the validation losses so far? And what index? So how many batches have we done, right? Well, the number of batches we've done is the number of batches which are passed through when we're training in one epoch. So that is the length of the train loader multiplied by the number of epochs we've done, right? Yeah, so number of multiplied by epoch, and that index is basically needed so that it plots in the right place. Okay. Yep, cool. So there's all that plotting stuff down there. Now should be able to go. Let's do this. Let's run this thing. Okay, so where's the errors coming from firstly? What is this? It's in the prediction criterion. So the size of the tensor must match the size of the tensor A must match the size of the tensor B. So okay, right. So let's just looks like our output is the wrong size. So let's print x dot shape. Run that. That's 416 by 4. Well, that's not quite right, is it? What does it come in as? Okay. So yeah, it comes in as 4 by 3 by 128 by 128. Well, all right. Sorry guys, maybe my maths was wrong. So let's do okay. Well, let's so we know we've just for a test, we know that we've got 4 examples in the first batch. So say, okay, I don't care what the shape should be on the other end, and then we'll print x dot shape. Just break that. Okay, cool. So apparently we've got 346,312 items in there. Okay, cool. Right. So what we should have to do is put that number here, 346,112, right there. So let's just print that shape there. Oh yeah, I've already got up here. Okay, cool. Right, so that's how many activations we should have in each of the batches, in each of the feature map stacks and the final output layer of the convolutional layers of the model. So what we can do is we can actually calculate that here. So we can say the width height of the X should equal, well, we don't really want to do that because it'll just take computation during runtime. So, okay, cool, right, we'll just put that number here then. We'll say 3461112. That's how many numbers we should get input to the convolutional layers. And then that should work. Let's try it. Oh no, we're printing all the names of the images as we go. Don't want to do that. Just be annoying. Stuff for that debugging. Okay. Let's run that then. See what happens. So a good guess to start with. What is going to happen if the loss should be going down, shouldn't it? There's a hell of a lot of, there's a relatively large amount of examples in this data set, so it'd be extremely surprising if it's doing it at all well over only 100 examples. So let's increase the batch size. That's taking way longer to do one pass through, isn't it? But the update will be based on the loss for all of those images in that batch, for those 64 images in that single batch. God damn. Let's make it smaller, see what happens. Okay, yeah, cool, right, so is that going to be the number? Yeah, so I obviously forgot to square it when I tried to calculate it earlier. I trust that my math was right. Indeed. Okay. By 32 by 8. So what we can do is we can do sorry, should be 32 by 8 by 8. Okay, run it. Come on. So yeah, this show function in the S40 dataset as well, it can take in an optional predicted bound box, so that you can visualize what your predictions are doing as well. and we'll do that after we've done training this, which we won't have time for. Okay, not learning very much. So I had a diagram of this loss plot after I'd done a bunch of training before, but I can't find it right now. But this is a hard problem, right? It's like, this isn't easy, and you shouldn't really expect at least this model to be able to perform after only having seen, so batch size 64 times 100 examples. But if you tune the parameters, what you'll see is a really noisy loss curve. But over time, if you give this a while, I trained overnight before, you see the loss drop. It is gradual, so it's hard to observe here. It's hard to even tell if it's learning at all. But we should try and do some stuff to accelerate that as well. So yeah, there you go. So it went into evaluation mode there. Yeah, if we'd have done that for more epochs, it would have plotted that those evaluation losses for the evaluation validation for the validation set on that graph as well, and you should hopefully be seeing those losses go down. And what they are the losses of the model on examples which it hasn't seen yet. And at the end, we did p.show. And we saw, the forward pass averagely took 1/10,000th of a second, and it was called 120 times over that first epoch. So yeah, please, we'll upload this now. Go away, use this code, try and tune the hyperparameters and find some good settings for it. See if you can get to learn, see if you can figure out how to visualize your predicted bounding boxes as well. But other than that, that was good. I hope that was educational. Another day, another hustle, another day of the month of ML. Thank you, and Hacker Hustle out.